Picture a machine older than most people alive today, hurtling through absolute darkness at 17 kilometers every second. No headlights, no cameras peering into the void ahead, just a collection of instruments from the 1,970 seconds, transmitting faint whispers across a distance so vast that each message takes more than a day to reach home. This machine is Voyager 1, and right now it occupies a place in the universe that defies every simple diagram you've ever seen of our solar system. We've all learned the basics. The sun at the center, planets arranged in neat orbits, maybe an asteroid belt, perhaps some mention of distant, frozen rocks tumbling beyond Neptune. Clean, contained, finished. But that picture, it turns out, was never complete. Because beyond the last planet, beyond the realm where sunlight gives way to perpetual twilight, there exists a frontier that wasn't supposed to behave like a frontier at all. A boundary that, according to early predictions, should have been straightforward, predictable, almost boring. Instead, what Voyager found there keeps rewriting the textbooks. This isn't a story about what scientists expected to find. It's about what actually exists out there in a region of space so remote that nothing humans have ever built had touched it until recently. And the strange part, the part that keeps researchers awake at night studying decades-old data streams, is how much this boundary refuses to sit still. It bends, it ripples, it responds to events happening billions of kilometers away, sometimes years after those events occurred. The edge of the solar system, as it turns out, is alive in ways no one predicted. So what exactly is Voyager crossing through? What makes this region, which every model suggested would be empty and featureless, so persistently strange? And why does a spacecraft built before personal computers, before the internet, before most of the technology we take for granted today, remain the only source of answers to these questions? The journey began in 1977, when two identical spacecraft lifted off from Earth with a single focused mission. Voyager 1 and Voyager 2 were designed to visit the outer planets, taking advantage of a rare planetary alignment that happens only once every 176 years. They would fly past Jupiter and Saturn, capturing close-up images and measurements, then continue onward into deep space. The mission timeline called for 4 years. Maybe 5 if the hardware held up. After that, the spacecraft would simply coast into the dark, their work complete, their purpose fulfilled. But those initial planetary encounters revealed something unexpected about the spacecraft themselves. They were tougher than anyone realized. The instruments kept working. The power systems kept generating electricity. The trajectory that was supposed to carry them into quiet retirement instead carried them towards something far more significant than a handful of planet flybys. Voyager 1 swung past Jupiter first, sending back images of roiling storm systems larger than Earth itself. It photographed Io, a moon tortured by volcanic eruptions so violent they spray material hundreds of kilometers into space. It revealed Europa's fractured ice shell, hinting at an ocean beneath. Then came Saturn, with its intricate ring system resolved in unprecedented detail. Voyager 2 followed a different path, one that would take it past Uranus and Neptune, worlds so distant that sunlight reaching them is barely distinguishable from starlight. It captured the blue-green haze of Neptune's atmosphere. It found geysers erupting from Triton's frozen surface, nitrogen ice vaporizing into plumes that defy the moon's weak gravity. These were discoveries that reshaped planetary science, images that filled textbooks for generations. And then, with their primary mission complete, both spacecraft just kept going. They climbed out of the planetary plane, carried by the gravitational momentum they'd borrowed from the giant worlds they'd visited. Voyager 1 angled upward, moving faster, pushing toward the northern reaches of the solar system's outer limits. Voyager 2 took a shallower trajectory, angling downward and southward at a slightly slower pace. By November 2025, Voyager 1 had reached a distance of 169 astronomical units from the Sun. To put that in perspective, 1 astronomical unit is the distance between Earth and the Sun, roughly 150 million kilometers. Voyager 1 is now 169 times farther from the Sun than we are. Voyager 2 trails at 139 astronomical units, but it's not simply behind. It's in a completely different direction, probing a different section of the boundary that surrounds our star's domain of influence. Both spacecraft are moving through a realm that doesn't belong to the Sun anymore, not in the way we usually think about the solar system, but they're not yet fully in the open galaxy either. They're in between. And that in-between zone, it turns out, is where things get profoundly strange. For decades, the edge of the solar system existed only as a theoretical construct. Scientists knew the sun constantly releases a stream of charged particles, a wind of protons and electrons that flows outward in all directions at supersonic speeds. This solar wind fills an enormous bubble around the sun, a protective cocoon that shields the inner solar system from the full intensity of cosmic radiation streaming through the galaxy. That bubble is called the Heliosphere, and somewhere far beyond the planets, it has to end. The solar wind can't push outward forever. Eventually, it runs into resistance from the interstellar medium, the thin gas drifting between stars. Where those two forces meet, where the outward pressure of the solar wind finally balances against the inward pressure of the galaxy, that's the heliopause. The border. Early models treated this boundary as a simple shell, a clean dividing line between two distinct regions. Inside, you'd measure particles and magnetic fields dominated by the sun. Outside, you'd measure the properties of interstellar space. The transition, most scientists assumed, would be relatively sharp but unremarkable. A spacecraft would cross it, the instruments would register the change, and that would be that. A data point, a milestone. Nothing more. But when Voyager 1 approached that boundary in 2012, what it actually encountered shattered those expectations. The spacecraft had been watching the solar wind slow down for years, a gradual deceleration as it pushed against the increasing pressure from outside. The magnetic field around the probe started organizing itself, aligning in ways that suggested structure forming ahead. Then, suddenly, the particle readings flipped. High-energy cosmic rays from the galaxy, which had been largely blocked by the sun's magnetic shield, surged dramatically. At the same time, the lower-energy particles from the sun, which had surrounded the spacecraft for its entire journey, nearly vanished. It wasn't gradual. It wasn't smooth. It was a transition that happened over the course of a single day, as if Voyager 1 had stepped off a cliff into a completely different environment. That sharp edge told researchers something crucial. In that particular direction, the heliopause wasn't a fuzzy transition zone. It was a boundary with real, measurable structure. 6 years later, Voyager 2 crossed the same boundary, but its experience was different. The cosmic ray levels increased, yes, but more gradually. The magnetic field shifted, but along a different angle. The transition felt less like falling off a cliff and more like descending a slope. Same boundary, different character, and that difference revealed something profound about the shape of the heliopause itself. It's not a perfect sphere. It's not even close. It bends and stretches depending on the direction, responding to the pressure of the interstellar wind pushing against it from one side, warping in response to the sun's own magnetic complexities. Both crossings shared one undeniable truth. The environment on the other side didn't resemble the environment inside at all. Once each spacecraft stepped across, everything changed. The plasma density outside the heliopause is actually higher than inside, despite the fact that the region feels emptier in almost every other sense. The magnetic field beyond the boundary is steadier, more organized, but it points in a completely different direction, no longer dominated by the sun's influence. Cosmic ray levels are significantly higher because the heliosphere's protective shield no longer blocks them. And then there's something else, something that took scientists by surprise even after they'd prepared for strangeness. The boundary reacts. It responds to events happening deep inside the solar system, billions of kilometers away. When the sun experiences a burst of activity, a coronal mass ejection, or a surge in solar wind intensity, that disturbance propagates outward like a wave. Months or even years later, the Voyagers detect it at the heliopause. They feel it as a sudden increase in plasma wave activity, a spike in density, or a ripple in the magnetic field. The boundary breathes. Slowly, ponderously, across timescales measured in seasons and years, it expands and contracts in response to the sun's moods. This revealed something fundamental. The heliopause isn't frozen in place. It's not a static line drawn in space. It's a dynamic interface between two opposing forces, constantly adjusting to shifts in pressure from both sides. And that means the edge of the solar system isn't really an edge at all. It's a living boundary, a zone of interaction that changes its shape, its thickness, and its behavior depending on what the sun is doing and what the galaxy is throwing at it. Before Voyager, scientists imagined the heliopause as thin, almost like the skin of a balloon. the spacecraft revealed something far more complex. There are layers within the boundary, regions where particles from the sun leak through into interstellar space, regions where the magnetic field twists into complicated geometries, regions where the sun's influence fades unevenly. The boundary has structure, depth, and variability. It's not a surface, it's a frontier, and perhaps most surprising of all, interstellar space itself, the region beyond the sun's protective bubble, didn't turn out to be the calm, silent void that early imagination suggested. Both spacecraft found turbulence out there, shocks from past solar events still propagating through the interstellar medium, variations in particle flow that weren't predictable from models. The quiet emptiness everyone expected simply wasn't there. Instead, Voyager found a space that's dynamic, responsive, and far stranger than the textbooks had room for. These discoveries didn't just add detail to our maps. They fundamentally changed the way scientists think about where the solar system ends and how our star interacts with the vast ocean of space surrounding it. The Heliopause crossing wasn't simply a milestone in exploration. It was the moment when theory met reality, and reality turned out to be far more complicated, far more interesting, and far more alive than anyone had dared to predict. But crossing the Heliopause, as monumental as it was, is only the beginning of Voyager's true journey. At their current speeds, these spacecraft will need roughly 300 years just to reach the inner edge of the Oort Cloud, that vast, diffuse shell of icy bodies where the sun's gravitational influence finally begins to weaken in earnest. Passing through the Oort Cloud's farthest reaches could take another 30,000 years. Only then, tens of thousands of years from now, will Voyager 1 and Voyager 2 finally leave our stellar neighborhood behind and become true wanderers of the galaxy. Right now, though, they're in a place no human-made object has ever been, and the data streaming back from that place, faint and slow as it is, continues to reveal secrets about a boundary that refuses to behave the way we thought it would. One of the most counterintuitive discoveries waiting beyond the Heliopause involves temperature. When Voyager 1 first crossed into interstellar space, its instruments detected plasma oscillations that revealed something unexpected about the material surrounding it. The plasma was hot, extraordinarily hot, tens of thousands of degrees hot. When that data first reached Earth, it sounded dramatic, almost apocalyptic. But temperature in space operates under fundamentally different rules than temperature on Earth, and understanding that difference is crucial to grasping what Voyager actually found. Temperature, as we experience it, measures the average kinetic energy of particles in a substance. On Earth, air and water are densely packed with molecules constantly colliding with each other, transferring energy through contact. When something is hot here, it means trillions upon trillions of particles are moving rapidly and can transfer that energy to your skin, to a thermometer, to anything they touch. But in the near vacuum beyond the Heliopause, density drops to almost nothing. The plasma Voyager detected is indeed hot in the sense that individual particles are moving at tremendous speeds, but there are so few of them per cubic meter that they carry almost no ability to transfer that energy to anything else. Imagine standing in a room where a single grain of sand flies past you at supersonic speed once every hour. That grain is moving fast, carrying significant kinetic energy, but you'd never feel it. You'd never register heat. The environment would feel empty, cold, inert. That's closer to what Voyager experiences in this hot plasma region. The particles are energetic, but they're so sparse that the spacecraft doesn't feel anything in the ordinary sense. No component heats up. No instrument is in danger. The energy is real, but it's diffused across such enormous volumes of space that it becomes almost abstract. Voyager 1 first detected this hot plasma through the vibrations it creates. When disturbances pass through plasma, they generate oscillations, waves that propagate like ripples on a pond. The frequency of those oscillations depends on the plasma's density and temperature. By measuring the frequencies, scientists could work backward to determine the conditions of the plasma itself, and those calculations revealed temperatures far higher than anything inside the heliosphere. Later, when Voyager 2 crossed the Heliopause in a completely different direction, it detected the same phenomenon. That confirmed this wasn't a local anomaly. The hot plasma layer wraps around the entire heliosphere, a feature of the boundary itself. The reason this layer exists has everything to do with the collision happening at the Heliopause. Inside the heliosphere, the solar wind flows outward at hundreds of kilometers per second, a supersonic stream of charged particles pushed by the sun's magnetic pressure. As this wind reaches the edge of the sun's domain, it slams into the interstellar medium, the thin gas drifting through the galaxy. That collision isn't gentle. The solar wind doesn't simply stop. It compresses, heats, and churns as it pushes against the incoming pressure from outside. Think of it like air being forced into a smaller and smaller volume. Compression raises temperature. In this case, the compression happens on a scale almost impossible to visualize. Billions of cubic kilometers of space, filled with plasma moving at extreme speeds, pressing against the boundary between two cosmic domains. The result is a layer where particles get squeezed together, where their velocities increase, where temperatures spike to levels that sound dramatic but exist in a medium so sparse it barely qualifies as matter by terrestrial standards. Both spacecraft discovered that this hot plasma region isn't uniform. Some areas are hotter than others. Some sections are thicker. The readings fluctuate over time, sometimes spiking, sometimes dipping, revealing that this isn't a static layer frozen in place. It shifts and responds to changes happening deep inside the solar system. When the sun erupts with a powerful coronal mass ejection, that burst of energy propagates outward, eventually reaching the heliopause. When it arrives, it slams into this hot plasma layer and heats it further. The Voyagers detect these changes long after the original solar event, catching the echoes of disturbances that began months or years earlier. The travel time alone tells you something profound about the scales involved. A shockwave from a solar storm, moving at hundreds of kilometers per second, still takes months to cross the vast distance between the sun and the heliopause. By the time Voyager's instruments register the impact, the event that caused it is ancient history back on Earth. And yet, out there at the boundary, the effects are still unfolding, still rippling through the plasma, still reshaping the structure of the heliopause itself. The magnetic field in this region adds another layer of complexity. Instead of pointing smoothly in one direction, it bends and twists, creating pockets where particles get trapped and accelerated. These magnetic tangles help explain why the boundary behaves so differently depending on where you cross it. Voyager 1, crossing in one direction, encountered more abrupt changes. Voyager 2, crossing elsewhere, found smoother transitions. The hot plasma layer isn't a perfect shell. It has uneven pockets, regions where the compression is stronger, areas where the magnetic field creates turbulence that heats the plasma even more. What makes this discovery so important isn't the temperature itself, it's what the temperature reveals about the nature of the heliopause. Before Voyager, many models treated the boundary as a simple interface, a line where one environment ended and another began. The hot plasma layer shows that the heliopause is far more complex than that. It's a zone of active interaction, a region where two fundamentally different environments grind against each other, creating conditions that don't exist anywhere else in the solar system. Understanding this layer also helps scientists see the heliosphere as a dynamic system. The sun isn't just sitting at the center of a static bubble, it's constantly pushing outward, and the galaxy is constantly pushing back. The heliopause is the battleground where those two forces meet, and the hot plasma layer is the signature of that ongoing collision. Even though the changes happen slowly, measured in months and years rather than seconds and minutes, the boundary is always reacting, always adjusting, always responding to the push and pull of cosmic forces operating on scales that dwarf human intuition. And here's the remarkable part. Voyager is measuring all of this with instruments designed and built in the 1,970 seconds, long before anyone had any direct data about what interstellar space actually looked like. The engineers who designed those instruments couldn't have known they'd be detecting plasma oscillations in a region beyond the sun's magnetic influence. They couldn't have anticipated the specific conditions their probes would encounter. They simply built the instruments to be as robust and flexible as possible, capable of measuring basic properties of space, regardless of environment. That design philosophy, grounded in simplicity and durability rather than cutting-edge complexity, is the reason Voyager can still do science in a place no one imagined it would reach. The hot plasma discovery also reshaped scientists' understanding of how the sun interacts with the surrounding galaxy. The heliosphere isn't just a protective bubble. It's an active interface where the sun's influence is constantly negotiating with the interstellar medium. The shape of that negotiation, the thickness of the boundary, the temperature of the plasma layer, all of these factors depend on the balance between internal and external pressures. And that balance can shift. Solar activity cycles through peaks and valleys over an 11-year period. During solar maximum, the sun releases more energy, more particles, more magnetic disturbances. During solar minimum, activity drops. These cycles affect the pressure pushing outward from the sun, which in turn affects the heliopause. The boundary swells slightly during active periods and contracts during quiet ones. The Voyagers are positioned to detect these slow, massive changes, watching the heliopause breathe over timescales that no mission limited to a few years could ever observe. The fact that both spacecraft are still operational, still sending data, still measuring the environment around them after nearly 50 years in space is not an accident. It's the result of extraordinary engineering, yes, but also extraordinary luck in the sense that nothing catastrophic has happened to either probe. No micrometeorite impact severe enough to damage critical systems. No onboard failure that couldn't be worked around. No loss of signal during a critical moment when engineers were implementing a software patch billions of kilometers away. But even with all that fortune, the mission is running on borrowed time. The radioisotope thermoelectric generators that power both spacecraft decay steadily, losing a few watts of output every year. What once provided ample electricity to run every instrument simultaneously now barely supplies enough to keep a handful of systems alive. Engineers have spent years carefully shutting down heaters, turning off backup circuits, sacrificing instruments one by one to stretch the remaining power as far as possible. Some components are now operating at temperatures far below their design specifications. Instruments that were never tested in such cold environments continue functioning anyway, defying expectations. The heaters that once kept them warm are long since disabled, sacrificed to save power. The spacecraft are colder than they were ever supposed to be, running on less energy than anyone thought possible. And yet, they keep working. This is the delicate balancing act that defines Voyager's current existence. Every decision about which system to keep active and which to shut down is made with the knowledge that there's no going back. Once something is turned off, the cold of space may prevent it from ever being reactivated. Engineers weigh every choice carefully, prioritizing the instruments that provide unique data, the systems that can't be replaced by anything else. And they do it knowing that each year brings less power, fewer options, and a narrower margin for error. The hot plasma layer, the dynamic heliopause, the interplay between solar wind and interstellar pressure, all of these discoveries exist because Voyager survived long enough to reach a place it was never designed to study. And all of them will continue to shape our understanding of the solar system's edge long after the spacecraft themselves fall silent. Even after nearly 5 decades of continuous operation, both Voyager spacecraft remain active scientific platforms, quietly gathering data from a region of space no other human-made instrument has ever reached. The measurements they collect are simple by modern standards. No high-resolution cameras, no sophisticated spectrometers, just fundamental readings of magnetic fields, plasma waves, and particle counts. But that simplicity is precisely what makes the data valuable. These are direct measurements of interstellar space near the sun, and nothing else can provide them. The magnetometer on each spacecraft continues to track the behavior of magnetic fields in their respective locations. Inside the heliosphere, the magnetic field is shaped and dominated by the sun, twisted into complex spirals by the rotation of our star and the outward flow of the solar wind. Outside the heliopause, that solar influence fades almost entirely. The field that Voyager measures beyond the boundary follows the structure of the galaxy itself, organized by forces operating on scales vastly larger than our solar system. Because Voyager 1 and Voyager 2 are positioned in completely different directions, their magnetic field readings provide 2 distinct perspectives on how the galactic magnetic field bends around the heliosphere. Voyager 1, farther out and in the northern direction, often detects a more consistent magnetic orientation, suggesting the field in that region is relatively stable. Voyager 2, crossing to the south, measures slightly different angles and occasional turbulence, revealing that the magnetic environment isn't perfectly uniform. Together, these 2 data streams help scientists map how the sun's magnetic bubble interacts with and distorts the surrounding galactic field. Plasma wave detection remains one of the most crucial capabilities both spacecraft still possess. The instruments can't directly measure plasma density anymore. Those sensors failed long ago, but they can detect the vibrations that plasma creates when disturbed. When shockwaves from solar events or turbulence in the interstellar medium sweep past the spacecraft, the plasma around them oscillates, generating waves at specific frequencies. Voyager's plasma wave instruments pick up these oscillations, and scientists can use the frequency data to calculate the density and temperature of the surrounding plasma. This technique revealed one of the most surprising aspects of the region beyond the Heliopause. The plasma density outside is actually higher than expected, denser than the thinning solar wind inside the Heliosphere's outer reaches. That discovery contradicted early assumptions that interstellar space would be emptier. It also showed that the density isn't constant. It varies from year to year, sometimes spiking when a disturbance passes through, sometimes dropping during quieter periods. These fluctuations provide clues about the dynamics of the interstellar medium itself, the slow currents and waves moving through the space between stars. Cosmic ray detection adds another critical dimension to Voyager's ongoing mission. These high-energy particles, accelerated by supernovae and other violent events across the galaxy, constantly bombard the solar system. Inside the heliosphere, the sun's magnetic field deflects and blocks many of them, providing a degree of radiation protection for the planets within. Outside the heliopause, that protection vanishes. Cosmic ray levels jump sharply once you cross the boundary, and Voyager's instruments track those increases with precision. By monitoring cosmic ray flux over time, researchers gain insight into how much shielding the heliosphere actually provides and how that protection varies with solar activity. During periods of strong solar output, the heliosphere expands slightly and the magnetic field strengthens, blocking more cosmic rays. During solar minimum, the opposite occurs. The boundary contracts, the shielding weakens, and cosmic ray levels rise even inside the heliosphere. Voyager's position outside the bubble allows scientists to measure the baseline cosmic ray environment, providing a reference point for understanding how much protection we lose as spacecraft venture beyond the sun's influence. The spacecraft also occasionally detect charged particles originating from the sun, even though both probes are now well beyond the heliopause. These particles arrive months or years after the solar events that produce them, carried outward by shock waves that propagate through the heliosphere and eventually disturb the plasma beyond the boundary. When Voyager's instruments register a sudden uptick in solar particles, scientists can trace the signal backward, correlating it with specific eruptions or coronal mass ejections that occurred long before. These delayed detections demonstrate just how far the sun's influence can still reach, even into interstellar space. The communication process itself has become a delicate, painstaking operation. At Voyager 1's current distance, radio signals traveling at the speed of light take more than 22 hours to reach Earth. Voyager 2's signals take slightly less time, but still more than 19 hours. That means every command sent to either spacecraft requires more than a full day to receive confirmation. If something goes wrong, if a command produces an unexpected result, engineers won't know about it until more than 40 hours have passed. Every decision must be made slowly, cautiously, with contingency plans in place for scenarios that might unfold while Earth is still waiting for the first response. The signals themselves are almost unimaginably faint by the time they reach Earth. Voyager's transmitters broadcast at roughly 20 watts, about the same power as a refrigerator light bulb. After traveling billions of kilometers spreading out across space, that signal arrives at Earth's deep space network antennas with a strength measured in billionths of a billionth of a watt. The antennas must be aligned with extraordinary precision, pointed at a specific patch of sky where the spacecraft should be, accounting for its motion and the time delay in receiving its signals. Even then, collecting useful data requires long observation sessions, carefully filtering out noise, extracting the tiny thread of meaningful information from the cosmic static surrounding it. If you're enjoying this journey into the nature of our solar system's edge, consider subscribing to our channel, Broken Zach, so you don't miss what comes next. The data rate has slowed to a crawl. In Voyager's early days, the spacecraft could transmit thousands of bits per second. Now, the rate has dropped to just 160 bits per second, a speed so slow that downloading a single modern photograph would take hours. But that limitation doesn't matter much anymore. Voyager isn't sending back pictures, it's sending numbers, measurements of magnetic field strength, plasma wave frequencies, particle counts, and those numbers require far less bandwidth than images. Even at this reduced rate, the spacecraft can transmit everything their remaining instruments detect. The Deep Space Network itself has become a critical bottleneck. These massive radio antennas located in California, Spain, and Australia are shared among dozens of active missions. Voyager doesn't get continuous coverage anymore. Engineers schedule observation windows, blocks of time when an antenna is dedicated to listening for Voyager's signal. During those windows, data flows back to Earth, and mission controllers monitor the spacecraft's health. Between windows, Voyager is on its own, continuing its journey in silence, storing data in its limited memory until the next contact opportunity. In 2025, this challenge intensified. Deep Space Station 43, the massive 70-meter antenna in Canberra, Australia, underwent critical upgrades. DSS-43 is the only antenna in the Southern Hemisphere powerful enough to send commands to Voyager 2, which is positioned below the plane of the solar system. While the antenna was offline for maintenance from May through February 2026, Voyager 2 effectively became receive-only. It could still send data back to Earth, but ground controllers couldn't send new commands. The spacecraft had to operate autonomously, following pre-programmed instructions, while engineers waited for the antenna to come back online. That period of reduced communication highlighted just how fragile the link between Earth and Voyager has become. These spacecraft are so far away, moving through such remote regions, that maintaining contact requires not just functioning spacecraft, but also functioning ground infrastructure. And that infrastructure is aging too, requiring upgrades and repairs to keep pace with the demands of deep space communication. What makes the current data stream so meaningful isn't its volume or complexity. It's the fact that it exists at all. Every measurement Voyager sends back represents information that cannot be obtained any other way. No telescope on Earth or in orbit can detect the local magnetic field at the Heliopause. No remote sensing technique can measure plasma density in situ billions of kilometers away. No model, no matter how sophisticated, can fully predict the turbulence and variability of the interstellar medium without direct observations to validate it. The numbers Voyager transmits are raw and simple, but they form the foundation for understanding a part of the universe we've barely begun to explore. They reveal how the heliosphere responds to solar cycles, how the interstellar medium fluctuates over time, how cosmic radiation varies with distance from the sun. They provide baseline measurements that future missions will use as reference points, benchmarks against which new observations can be compared. And, perhaps most importantly, they demonstrate that even old technology, built with outdated materials and primitive electronics by today's standards, can continue producing valuable science if it's engineered with durability and flexibility in mind. Voyager's instruments were never designed to operate at the temperatures they now endure. They were never tested for missions lasting 5 decades. They were built to survive a 4-year tour of the outer planets, and everything since then has been an extension, an unexpected gift of data from a region no one imagined these spacecraft would reach. The fact that both Voyagers are still transmitting, still measuring, still contributing to our understanding of space is a testament to the engineers who built them and the teams who've kept them alive. But it's also a reminder that exploration doesn't always require the latest technology. Sometimes it just requires the patience to keep listening, the skill to work around limitations, and the willingness to learn from instruments that refuse to quit. Keeping the Voyager spacecraft operational has evolved into something far more complex than anyone anticipated when they launched in 1977. The mission was supposed to last 4 years, maybe 5, if everything went perfectly. No one designed these machines to survive half a century in the harshest environment imaginable. And yet here they are, still transmitting, still measuring, still doing science at the edge of interstellar space. But that survival comes at a cost, and the cost grows steeper every year. The fundamental problem is power. Each spacecraft carries 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity. When Voyager launched, these generators produced roughly 470 watts combined, more than enough to run every instrument, every heater, every system simultaneously with power to spare. But plutonium-238 decays steadily, and as it decays, it produces less heat. Less heat means less electricity. The decline is predictable, inevitable, and irreversible. By 2025, each spacecraft generates only about 220 watts, less than half its original output. And that number drops by roughly 4 watts every year. In the early decades of the mission, this decline didn't matter much. Engineers had plenty of margin. They could afford to run redundant systems, keep backup circuits active, maintain thermal control across the entire spacecraft. But as the power budget tightened, every watt became precious. The mission team faced a long series of difficult decisions: which instruments to keep running, which heaters to disable, which systems to shut down permanently to conserve energy for the instruments that still produce unique science. The heaters were among the first casualties. Voyager's electronics were designed to operate within specific temperature ranges, and heaters were installed throughout the spacecraft to maintain those ranges in the cold of deep space. But heaters consume significant power, and as the available electricity dwindled, they became luxuries the mission could no longer afford. One by one, over the course of years, engineers turned them off. The instruments got colder, the electronics got colder. Components that were never tested at such low temperatures continued operating anyway, functioning far outside their original specifications. In some cases, instruments are now running at temperatures dozens of degrees below what their designers believed was the absolute minimum for survival. The fact that they still work is partly good fortune, partly a testament to the engineering conservatism of the 1,970 seconds. Components were built with margins. Tolerances were generous. The engineers who designed Voyager didn't know exactly what conditions the spacecraft would face, so they built in as much robustness as weight and budget allow. That philosophy is paying dividends decades later, but the cold creates its own problems. In May 2025, the mission team faced a crisis with Voyager 1's attitude control system. The spacecraft uses small thrusters to keep its antenna pointed precisely at Earth, making tiny adjustments to compensate for the slow drift that accumulates over time. These thrusters rely on fuel lines that must remain liquid. If the fuel freezes, the thrusters become useless, and the spacecraft can no longer maintain its orientation. Without correct orientation, the antenna doesn't point at Earth, and communication is lost permanently. Voyager 1's primary thrusters had been offline since 2004 because the heaters that kept their fuel lines warm had failed. For years, the spacecraft relied on backup thrusters, but by 2025, even those were showing signs of strain. The fuel lines were getting dangerously cold, approaching temperatures where the fuel might solidify. Engineers knew they had to act. They spent weeks analyzing data, reviewing decades-old documentation, planning a delicate operation to reactivate the primary thrusters by remotely toggling power switches deep within the spacecraft's electrical system. The maneuver worked, but it was a close call. The primary thrusters came back online just in time, preventing a fuel line rupture that would have ended the mission. But the episode highlighted how precarious Voyager's situation has become. The spacecraft is running on components that were never meant to function in these conditions, maintained by engineers sending commands across billions of kilometers, waiting more than a day for each response, troubleshooting problems with hardware built before most of them were born. Memory corruption presents another ongoing challenge. Voyager's computers use technology from the early 1,970 seconds, memory chips that store data as magnetic states on tiny cores of ferrite material. This core memory is more robust than early semiconductor memory, less susceptible to radiation, but it's not invulnerable. Cosmic rays, high-energy particles streaming through interstellar space, occasionally strike the memory chips and flip bits, changing zeros to ones or ones to zeros. A single corrupted bit in the wrong location can cause the spacecraft to misinterpret a command, execute the wrong instruction, or fail to transmit data correctly. In April 2025, engineers finally resolved a particularly stubborn memory problem that had plagued Voyager 1 for months. A corrupted chip in the flight data subsystem, containing just 3% of the system's code, had been causing garbled telemetry. The spacecraft was still gathering data, but it couldn't format that data correctly for transmission. For months, mission controllers received gibberish instead of useful information. The fix required locating ancient blueprints from the 1,960 seconds, understanding exactly how the memory was organized, and carefully relocating the affected software to unused sections of RAM that weren't corrupted. The process was painstaking. Engineers had to write new commands, test them virtually on ground-based simulators, transmit them to Voyager, and then wait more than 2 days for confirmation that the commands had worked. If something went wrong, if the relocation caused a new problem, they wouldn't know until another 2 days had passed. Every step had to be planned with extreme care, every contingency anticipated, because mistakes at this distance are difficult or impossible to reverse. Even the communication infrastructure on Earth has become a limiting factor. The deep space network antennas that receive Voyager signals are aging themselves. They require maintenance, upgrades, and occasional complete overhauls. When Deep Space Station 43 Inches Australia went offline for upgrades in 2025, it left Voyager 2 temporarily unable to receive commands. The spacecraft could still transmit data, but ground controllers couldn't send new instructions. Voyager 2 had to operate autonomously for months, following pre-programmed routines, while the antenna underwent critical improvements. This situation will only become more constrained as time passes. The deep space network is stretched thin, supporting missions across the solar system. Voyager competes for antenna time with newer missions, more complex missions, missions that require more frequent communication. As Voyager's power continues to decline and its instruments are shut down one by one, the allocation of DSN resources will likely decrease as well. The spacecraft will receive fewer observation windows, less frequent communication opportunities, longer gaps between contacts. The insulation around Voyager's wiring has also degraded over time. Decades of exposure to temperature swings, radiation, and vacuum have taken their toll on materials that were never meant to last this long. Engineers can't repair physical damage. They can't replace worn components. All they can do is adapt, routing signals through backup circuits when primary pathways fail, adjusting command sequences to avoid triggering faults, reducing activity during periods when the spacecraft shows signs of stress. Sometimes the best solution is simply to do less. When a system behaves erratically, engineers give it time to stabilize before sending the next command. When power levels drop too low, they shut down non-essential functions and wait for conditions to improve. This isn't active repair. It's careful management of a machine that's falling apart in slow motion, trying to extract every last piece of useful data before the inevitable silence arrives. The prioritization of instruments has become ruthlessly pragmatic. Voyager 1 now operates only 3 instruments: the magnetometer, the plasma wave detector, and the low-energy charged particle detector. Everything else has been shut down to conserve power. Voyager 2 has the same 3 active instruments, plus a cosmic ray detector that's scheduled to be turned off within the next year. These 4 instruments, out of the 10 or more each spacecraft carried at launch, are all that remain. They were chosen because they provide data that can't be obtained any other way, measurements that are scientifically irreplaceable given Voyager's unique position in space. Every decision about what to keep running and what to sacrifice is made with the understanding that the clock is ticking. Each year brings less power. Each year brings lower temperatures. Each year increases the probability that some critical component will fail, that some system will degrade past the point of workaround, that the long chain of contingencies and adaptations that have kept Voyager alive will finally run out of options. The engineers managing this mission aren't working with cutting-edge technology. They're working with decades-old hardware, incomplete documentation, and the accumulated knowledge of teams who've spent their entire careers learning the quirks and limitations of these 2 spacecraft. They're performing a kind of archaeological engineering, reverse engineering systems built by people who've long since retired, finding creative solutions to problems no one anticipated when Voyager was designed. And through all of this, both spacecraft keep transmitting. The data stream is thin, the communication windows are limited, the instruments are few, but the measurements keep coming. Magnetic field readings, plasma wave detections, particle counts, simple numbers that describe a region of space no other instrument has ever touched. That's what makes this mission valuable now. Not the grandeur of planetary flybys, not the stunning images that filled textbooks, just the quiet, persistent accumulation of data from a place where no one expected these machines to survive, let alone continue doing science. The fact that Voyager is still operational is not luck. It's the result of careful, deliberate engineering choices made nearly 50 years ago, combined with decades of skillful improvisation by mission teams who refuse to let these spacecraft fail as long as any option remains. But even with all that effort, the end is approaching. The power will run out. The instruments will fall silent. And when that happens, Voyager will transition from active science mission to silent monument. drifting through interstellar space with no way to report what it encounters, no way to send back the discoveries that may be waiting in the darkness ahead. When people think about Voyager's future, they often imagine a straightforward trajectory leading outward into the galaxy. The reality is far more complex and unfolds across timescales that dwarf human history. Both spacecraft have crossed the Heliopause, yes, but that milestone, as monumental as it was, represents only the first step in a journey that will continue for tens of thousands of years. The solar system, it turns out, extends far beyond the magnetic bubble where the solar wind holds sway. The next major region waiting ahead is the Oort Cloud, a vast spherical shell of icy bodies that surrounds the Sun at enormous distances. Unlike the asteroid belt or the Kuiper belt, which are relatively flat disks aligned with the planetary plane, the Oort Cloud is truly three-dimensional, wrapping around the solar system in all directions. It begins somewhere around 2,000 astronomical units from the Sun and extends outward to perhaps 100,000 astronomical units or more. To put that in perspective, Voyager 1, after nearly 50 years of travel, has covered only 169 astronomical units. It hasn't even come close to the inner edge of the Oort Cloud. Current estimates suggest it will take roughly 300 years for Voyager 1 to reach the inner boundary of this distant region. 3 centuries. Voyager 2, moving slightly slower and in a different direction, will take a bit longer. By the time either spacecraft reaches that milestone, everyone alive today will be long gone. The civilizations that launched these probes will have changed in ways impossible to predict, and the spacecraft themselves will be silent, their instruments powered down, their transmitters cold, drifting without any ability to report what they encounter. The Oort Cloud isn't dense. It's not a packed field of icy debris waiting to be navigated. It's almost unimaginably sparse. A diffuse collection of cometary nuclei spread across a volume of space so vast that the average distance between individual objects is measured in tens of millions of kilometers. The probability that Voyager will pass close to any Oort Cloud object is vanishingly small. These spacecraft aren't aimed at anything in particular. They're simply coasting along trajectories determined by the gravitational assist they received from Jupiter and Saturn decades ago. They'll pass through the Oort Cloud without incident, without detecting anything, without coming close enough to any icy body to even register its presence. But even though the Oort Cloud is empty in practical terms, it represents something significant. It marks the true extent of the Sun's gravitational dominance. Objects in the Oort Cloud orbit the Sun, but their orbits are so large and so slow that a single revolution can take millions of years. These are bodies that barely feel the Sun's warmth, that exist in a kind of perpetual deep freeze at the ragged edge of solar influence. And even here, even at these enormous distances, they still belong to the Sun in the gravitational sense. Voyager will spend approximately 30,000 years crossing the full extent of the Oort Cloud, 300 years to reach the inner edge, 30,000 to traverse the entire shell and emerge on the other side. During that immense span of time, the spacecraft will be dark and silent, coasting through the void with no power, no functioning systems, no connection to Earth. They'll simply exist as inert objects following ballistic trajectories through a region of space so remote that even light from the Sun is barely distinguishable from starlight. Only after passing beyond the Oort Cloud will Voyager truly leave the solar system in the fullest sense. The Heliopause marks where the Sun's magnetic influence ends. The Oort Cloud marks where its gravitational influence fades. Beyond that outer boundary, the spacecraft will no longer orbit the Sun. They'll become objects of the galaxy itself, moving through interstellar space with trajectories determined not by the Sun, but by the collective gravitational pull of the Milky Way. The paths both spacecraft will follow have been calculated based on their current velocities and directions. Voyager 1 is headed generally toward the constellation Ophiuchus, moving upward relative to the plane of the galaxy. In roughly 40,000 years, it will pass within about 1.6 light-years of a small, red dwarf star called Gliese 445. That might sound close, but 1.6 light-years is still an immense distance, roughly 10 trillion kilometers. Voyager won't encounter that star in any meaningful sense. It will drift past at a distance where the star is just another point of light among thousands, completely unaware of the ancient human artifacts sliding silently through the darkness nearby. Voyager 2 is traveling in a different direction, angled downward relative to the galactic plane. Its closest stellar approach will come in about 40,000 years as well, when it passes within a few light years of a star called Ross 248. Again, this isn't a flyby in the planetary sense. There will be no dramatic encounter, no moment of discovery, just two objects moving through the same general region of space, separated by distances that render them invisible to each other. What makes these projected paths interesting isn't what will happen, it's the sheer duration involved. 40,000 years ago, humans were living in small hunter-gatherer groups, just beginning to develop agriculture in a few isolated regions. 40,000 years from now, Voyager will be making its closest approach to another star, carrying with it a gold-plated record containing sounds and images from a world that will have changed beyond recognition, or perhaps ceased to exist entirely. The timescales involved make human intuition break down. We can calculate the trajectories. We can predict where the spacecraft will be in 10,000 years, 50,000 years, 100,000 years. But we can't truly comprehend what those numbers mean. The Voyager spacecraft will outlast nations, languages, possibly even the species that built them. They'll continue their journeys long after every trace of their creators has vanished from Earth. Silent monuments to a moment in human history when we first reached beyond our own star. And yet, despite the grandeur of that vision, the immediate future is far more mundane. The spacecraft aren't heading toward anything dramatic. They're simply moving forward, following the momentum they gained from gravity assists decades ago. Nothing will deflect them. Nothing will speed them up or slow them down in any significant way. They'll just drift, year after year, century after century, gradually increasing their distance from the sun at a steady, unchanging rate. The environment they're moving through won't change much either. Interstellar space near the sun is relatively uniform. There are no major obstacles ahead. No dense clouds of gas, no regions of intense radiation that might damage the spacecraft. The void they're crossing is profoundly empty, filled only with the thin interstellar medium and the occasional cosmic ray passing through. Even the magnetic field they're measuring will remain relatively stable, organized by the large-scale structure of the galaxy rather than the local dynamics of any particular star. In a practical sense, Voyager's journey forward is a journey into silence. The data transmissions will stop within a few years when the power finally runs out. After that, the spacecraft will coast through space without any way to communicate, without any ability to record what they encounter, without even the internal processes that keep their clocks running. They'll become inert, frozen relics of 1,970 seconds engineering, preserved by the vacuum of space, but stripped of any function. But even in that silent state, they'll continue to exist as physical objects, following trajectories that can be calculated with precision. Astronomers thousands of years from now, if such astronomers exist, will be able to predict Voyager's position with reasonable accuracy, tracking these ancient probes as they move through the galaxy. They might even attempt to recover them, sending faster spacecraft to intercept and retrieve these artifacts from an earlier era of exploration. Or they might simply let them drift. There's no compelling scientific reason to bring Voyager back. By the time recovery becomes technologically feasible, the spacecraft will be archaeological curiosities rather than functional instruments. They'll represent a snapshot of human capability in the late 20th century, a testament to what could be achieved with primitive electronics, mechanical gyroscopes, and radioisotope power sources. But they won't tell us anything new about the universe. That work will have been done decades or centuries earlier, by missions that followed in Voyager's wake. What Voyager's long future really represents is perspective. These machines will outlast everything familiar. They'll outlast the people who built them, the institutions that launched them, possibly even the political entities that funded them. They'll drift through the galaxy for millions of years, unchanged, silent, carrying their golden records inscribed with greetings in dozens of languages, music from a world that may no longer exist, images of life on a planet that may have transformed beyond recognition. In that sense, Voyager's journey isn't really about reaching a destination. It's about the act of moving forward, of continuing to exist in a universe that operates on scales far beyond human comprehension. The spacecraft will cross unimaginable distances, not through effort or intention, but simply because nothing stops them. They'll pass through regions of space that no one will ever visit, witness stellar configurations that no one will ever see, drift through epochs of galactic history that humanity might not survive to record. And through it all, they'll remain exactly what they were when they left Earth. Two machines built to explore, now freed from any purpose but existence itself, moving steadily into a future that extends far beyond the imaginable. The significance of Voyager today rests on something far more concrete than sentiment or historical curiosity. These spacecraft matter because of where they are and what they've revealed. For decades, scientists constructed models of the Heliosphere using indirect observations, measurements taken from inside the solar system, theoretical frameworks built on limited data. Those models were educated guesses, sophisticated but ultimately speculative. Voyager transformed speculation into fact. It showed what the boundary actually looks like, how it behaves, how it responds to forces acting across billions of kilometers. That transformation reshaped our entire understanding of how the Sun interacts with the galaxy. Before Voyager crossed the Heliopause, interstellar space was a theoretical construct, a region described by equations and assumptions but never directly measured. Now it's a place with known properties: plasma density, magnetic field orientation, cosmic ray flux, turbulence patterns. All of these are no longer abstractions. They're measured quantities, numbers recorded by functioning instruments operating in situ. That shift from theory to observation is fundamental to how science advances. Models can only take you so far. Eventually, you need data from the environment itself, and Voyager provided that data. The spacecraft also opened a region of space that future missions will need to understand. Any probe venturing beyond the Heliopause will be entering territory that Voyager mapped first. The baseline measurements these spacecraft collected become reference points, standards against which new observations can be compared. Without Voyager, those future missions would be navigating blindly, with no clear sense of what conditions to expect. With Voyager, they have context. They know what the transition looks like in at least two directions. They understand that the boundary is dynamic, uneven, and responsive to solar activity. That knowledge is foundational. Voyager's contribution to solar physics is equally important. The readings streaming back from beyond the Heliopause help confirm how far the Sun's protective influence extends and how effectively it shields the inner solar system from galactic cosmic radiation. Inside the Heliosphere, we're protected from the full intensity of high-energy particles that permeate the galaxy. Outside, radiation levels increase substantially. Understanding that difference is critical for planning any deep space mission, especially ones that might carry humans beyond the Moon or Mars. Voyager quantifies the radiation environment we'll face once we leave the Sun's protective bubble, providing data that's essential for designing, shielding, and assessing long-term exposure risks. The survival of these spacecraft also demonstrates something valuable about engineering philosophy. Voyager's instruments are simple compared to modern sensors. They lack the sophistication, the precision, the computational power of instruments launched in the 21st century. But that simplicity is part of why they still function. They were built with substantial margins, designed to handle unknown conditions, constructed with durability prioritized over cutting-edge capability. That approach has paid dividends for nearly 50 years. It's a reminder that exploration doesn't always require the most advanced technology available. Sometimes it requires robust, reliable technology that can survive long enough to reach places no one anticipated. There's another dimension to Voyager's importance that scientists don't ignore. These spacecraft hold the first direct measurements of the Heliopause, and those measurements will remain the primary reference for decades, possibly longer. Even when Voyager falls silent, the data already transmitted will continue to be studied, reanalyzed, integrated into new models as our understanding evolves. The field of heliophysics will return to Voyager's observations again and again, using them to test hypotheses about solar wind interactions, magnetic field structures, and the dynamics of boundary regions between stellar domains. Voyager also stands as the first human-made object to enter interstellar space. That fact doesn't add scientific information, but it marks a boundary in human activity, a threshold crossed for the first time. These spacecraft weren't designed to be symbolic. They were built to gather data, to perform measurements, to fulfill specific mission objectives. But their survival and their distance give them meaning beyond their original purpose. They're proof that a machine built for a 4-year planetary tour can end up far beyond its intended destination, still performing work that no newer mission can replicate. And then there's the practical matter of data that nothing else can provide. Every transmission from either spacecraft, no matter how limited, adds information to a map of the outer solar system that never existed before. Even a weak signal that takes more than a day to reach Earth carries knowledge about a place no one has visited. That alone justifies the mission's continuation. As long as the spacecraft can transmit, as long as the instruments can measure, the data they send back fills gaps that no other mission is positioned to address. When you consider where Voyager is now, it's easy to forget how ordinary the beginning was. 2 spacecraft built for a specific, time-limited mission, a planetary tour that was supposed to last a few years and then conclude. There was no grand plan for interstellar exploration. No expectation that these machines would outlive their design specifications by decades. They were expected to complete their work and drift into silence. Their purpose fulfilled, their story finished. Instead, they ended up in a region no one had mapped, measuring phenomena no one had directly observed, sending back information that continues to reshape scientific understanding of the solar system's edge. The interesting thing is how unremarkable the spacecraft themselves are when you strip away the distance. They're old machines running on failing power systems, carrying instruments that were never designed for the temperatures they now endure. They don't adapt. They don't repair themselves. They simply persist, doing what they were built to do for as long as the hardware allows. Thinking about their situation puts the scale of the solar system into sharp perspective. Voyager has been traveling for nearly half a century, and it has only just crossed the Heliopause. The Oort Cloud lies hundreds of years ahead, true interstellar distance. The kind measured in light years rather than astronomical units won't be reached for tens of thousands of years. Space doesn't open up in clean stages. It stretches out in vast, quiet distances that resist human intuition, that don't feel real until a spacecraft actually crosses them. Another quality that defines this mission is consistency. There have been no sudden course changes, no dramatic encounters that altered the trajectory, no moments where Voyager veered off into unexpected directions. Everything has been steady. The spacecraft keep moving forward. They keep transmitting whatever data they can. They keep outlasting predictions about when they'll finally fail. That slow, patient reliability is part of what makes the mission significant. It isn't about drama, it's about endurance. At some point, likely within the next few years, the transmissions will stop. There won't be a final message, no last observation marking the end. The power will simply drop below the threshold needed to run the remaining instruments and transmitters. The spacecraft will fall silent gradually, systems shutting down one by one as the available electricity becomes insufficient. After that, Voyager will continue moving through space with no connection to Earth, no way to report what it encounters, no sign that it was ever part of a mission. What remains after the signal fades is the accumulated record of everything already sent back. The measurements of the heliosphere, the data from interstellar space, the observations of how the boundary shifts and responds, the detection of hot plasma layers, the tracking of cosmic rays, all of it becomes part of the permanent scientific record. Future researchers will study this data when planning missions to the outer solar system. They'll reference Voyager's observations when modeling the interaction between stellar winds and the interstellar medium. They'll use these measurements as benchmarks when interpreting results from more advanced instruments. Perhaps the simplest way to understand Voyager's significance is this. It shows how far steady motion can carry something when given enough time. The spacecraft weren't built for the journey they're on now, but they're making it anyway. They weren't designed to study interstellar space, but they're the only machines doing it. They keep moving, not because of active propulsion or deliberate navigation, but because nothing stops them. That quiet momentum is the last characteristic they'll carry as they leave the solar system behind. One incremental distance at a time, the heliosphere will continue to shift and breathe long after Voyager stops measuring it. The plasma beyond the boundary will keep oscillating in response to solar events that occurred decades from now. The magnetic field will maintain its slow, steady organization, shaped by forces operating on galactic scales. And somewhere in that vast environment, 2 small machines will drift silently, no longer participants in the ongoing story of the sun's interaction with the galaxy, but markers of a time when humanity first reached far enough to touch that boundary directly. Voyager's journey reminds us that exploration isn't always about reaching a final destination. Sometimes it's about the act of moving forward, of continuing to exist in a universe that operates on scales beyond human lifetimes. These spacecraft will travel distances we can calculate but not truly comprehend. They'll pass through regions no one will visit. They'll witness configurations of space and matter that no one will record. And through it all, they'll remain exactly what they were when they left Earth. Machines built to explore, now freed from purpose, but not from motion, moving steadily into a future that extends beyond imagination. In the end, What Voyager leaves behind isn't just data. It's proof that we reached outward, that we built something capable of crossing boundaries we'd only theorized about, that we succeeded in touching a part of the universe we'll never visit ourselves. The spacecraft will outlast nations, technologies, possibly even the species that launched them. But before they fall silent, before they become nothing more than drifting relics, they'll have given us something irreplaceable. A direct look at the edge of our solar system, measured not with telescopes from a distance, but with instruments that traveled there and felt it firsthand. That's what makes Voyager matter. Not the distance alone, not the longevity, but the knowledge it brought back from a place we couldn't reach any other way. Knowledge that will shape our understanding of the sun, the heliosphere, and the space beyond for as long as we continue looking outward. If you enjoyed this video, watch this one too. It's a great one, and we'll see you in the next video.